This is unit 8.1, and in this section, we're going to be talking about calculating Ka and Kb. And if you remember from our last section, we were talking about the equilibrium constant, K, and we were talking about Keq and Ksp, the solubility product for the solubility of insoluble salts or soluble salts. Here, Ka is going to be specifically looking at the equilibrium constant of acids, that's the A, and B, that's the bases. So let's get started. In book 2, there's going to be pages 311 through 330. So remember, strong acids and strong bases dissociate 100%. I'm going to drag over our reference materials that we have, and I'm just going to remind you that there is a list for those, and that's right here, strong acids and strong bases. So if it's listed on this list, okay, that's a strong acid. Over here, strong bases. And this means that they dissociate 100%. So when they're placed in water or they're in water, that means that, for example, this hydrogen ion will split apart from this nitrate ion. 100% of those molecules, those compounds, those formula units will split apart. They'll no longer be together. And so that's for strong acids and strong bases. Well, most acids and bases are not considered to be strong. So it's just that short list there that I just showed you. And therefore, they only dissociate slightly in water. And this is represented generally as a general equation as this here. So for this equation, we see HA. That means hydrogen bonded to A. A is just any other ion that's bonded to this H. So that's the ion, A for ion. So we have an acid in water, okay? And what really happens is one of these hydrogens from this water are going to bond onto this, this hydrogen here from the acid is going to bond onto this water, okay, to produce H3O. And then what you have left is just the ion here. Now, this is what actually happens, but we represent that in just a slightly different way when we write out equations. This is positive, so it's sometimes represented as just H instead of H3O, but what actually happens is this hydrogen does bond to the water molecule, making H3O. Okay, so also remember that any equilibrium expression is represented by K. So we see that right here, and is the concentration of the products. So it's the concentration of the products, okay, multiplied together over the concentration of the reactants, okay, leaving out any liquids or any solids. Okay, so the equilibrium expression for this equation would be the concentration of H3O times the concentration of A divided by the concentration of HA. Okay, and we see that right here. Now, if we were to have any coefficients that were used to balance this, like say, for example, we had this coefficient here. Remember, this coefficient then becomes an exponent when you put it into the equilibrium expression. Okay, now this very exact same thing is going to be true for bases. Okay, bases have a generic equation. Here you have your base plus the water. Now what happens is one of these hydrogens from the water is now going to bond to the base. So that's why we have HB. It's a hydrogen bonded to this base. Normally, this hydrogen is going to come at the end of the base. So, for example, if we had, say, I have it written here, NH3. Okay, so one of these hydrogens is going to come over and bond. And so it's going to make NH4. And then what's going to be left over here is OH, and that's here represented as OH. Now remember, OH, hydroxides, are what makes a base a base. All right, so we have another example here, pyridine. So we have C5H5N. Okay, so we're going to combine it with water. It's going to be in water. So one of these hydrogens is going to leave the water and bond to the pyridine. And normally we put it at the end. So you see here it's at the end instead of at the beginning. At the end, plus what's left over is the OH. Okay. Now, many times, many times, as a shortcut, what you will see is this water being left out. Okay, so for example, if we were going to rewrite this equation and leave the water out, we would write C5H5N, okay, yields C5H5NH, just like this, plus the OH. Okay. So what we do is we just leave the water out. So the same thing kind of happens with an acid. So here we have this. So we'll have HA, okay, goes to H. So leaving the water out. So H2O off of this just leaves H plus A. So many times you'll see it written in the simplified form like this without the water. Okay. So you'll see that in your homework, and also you'll see it in some of the problems that I work out. All right, so the last thing that I want to mention is magnesium hydroxide. Magnesium hydroxide and beryllium hydroxide are special cases of hydroxides. And let me pull this over again and talk about it here. So they're not considered strong bases. So if we look here at our list of strong bases, this really is all of the alkali metals plus Ca, Ba, and Sr from group 2. So if we look at our periodic table, it's these alkali metals right here combined with hydroxide plus calcium, strontium, and barium that make your strong bases. So beryllium and magnesium really are not strong bases. They dissociate less than 100%, so that makes them considered as weak. But in our discussion of acids and bases, Ka and Kb, these are not used in that discussion. So when we're talking about Ka and Kb and the dissociation of weak bases, even though they're weak, we don't use those. We always use some other types of bases. So you won't see any problems with magnesium and beryllium in this course here. All right, so let's look at pyridine again, and let's write out the dissociation equation, the Kb for that. So remember, we're going to take our products, concentration of those, that's going to be what's going to be on top here, okay, multiplied together, divided by the concentration of the reactant on the bottom. So it's the same thing as what we used for the acid. Okay, no change there. Okay, so also in this section for the formulas for pH and pOH, we're going to continue to use those. So make sure that you have those handy. Make sure that you know what they are. So pH is the negative log of the hydrogen ion concentration. Now, this is the only formula that's provided for you on your reference materials. So those reference materials that you get to use on your quizzes, that one is really the only formula that's listed on the formula sheet. And let's pull that over and look for that real quick, just so you know where that is. Let's see. Well, here's the dissociation constant for water, Kw, hydrogen times hydroxide. The product of those two is 1.0 times 10 to the negative 14th, and we're going to be using that concept. And I think acids and bases may have their own little section. Oh, Right here, solubility shortcuts, we may be using that. All right, so here's solutions right here. So we have Kw again is this, which is equal to 1.0 times 10 to the negative 14th. We have dilution. Here it is. pH is the negative log. H, right here, pH and POH equals 14. And the concentration of the hydrogen is 10 to the negative pH. So it gives you a little more than I thought, but still it doesn't give you the hydroxide values for these, but it's the same equation. You just substitute in, instead of hydrogen here, you substitute in hydroxide. And instead of hydrogen here, you substitute in OH. So the concentration of OH is the 10 to the negative POH. Okay, so that's where those are right there. All right. All right, so for our first example, also what you're going to need is definitely this Ka table that I sent to you, linked into Canvas. You're going to also need this as you work out these problems and probably on the quiz as well. All right, so hydrogen sulfide is a poisonous gas whose rotten egg smell is perceptible at concentrations as low as 4.7 times 10 to the negative 4th parts per million. It's also a weak acid. So when dissolved in water, it becomes hydrosulfuric acid, okay, HS. So there you see it right there. And it says the pH of this is 0.05. Calculate the pH of a 0.050 molar solution of HS. All right, so if we look on our Ka table, we're going to see this right here, the dissociation equation, which we have written right here. Okay, this one does not contain water, but I wrote water here to show you how we do this, how it happens. And its Ka is 9.1 times 10 to the negative 8th. All right, so that Ka is going to be important. This is for hydrogen sulfide. Now, you may be thinking to yourself, well, this problem here says that it's hydrosulfuric acid. Well, hydrogen sulfide, when it's placed in water, becomes the aqueous form, the acid, so it's hydrosulfuric acid, hydrogen sulfide, same thing. All right, so it says here that we start out with the 0.050 molar solution of this. Okay, so we can go ahead and fill in our ice table. We're going to be using ice tables on this again. So water, liquid. Remember, we do not use liquids, so I'm going to put an X there. So we have our HS ion here and our hydrogen or H3O here. So remember, this is the same thing as the hydrogen ion. All right, so at the beginning, we're going to have 0 of this and 0 of this, right? This is going to change by some value. We're going to call that X. So it's going to go down by X because as it reacts, the change, it's going to go down by some value of X. Now, since this is 1 to 1 to 1, okay, in our balanced equation, this goes down by X. This is going to go up by X. And when we talk X, we're talking about molarity. Okay, molarity. Here, this is also going to go up by a value of X because it's 1 to 1. Okay, so here we need to find out what we have at equilibrium. Well, it tells us that that we're calculating the pH, and it also tells us that here we've got 9.1 times 10 to the negative 8 as our Ka. So I'm just going to write that information down. The Ka is equal to 9.1 times 10 to the negative 8. All right, so what is our equilibrium constant expression? It's going to be HS, the concentration of our HS, times the concentration of our hydrogen over the concentration of H2S. Okay, this is going to be equal to 9.1 times 10 to the negative 8th because this is the value for the Ka of hydrogen sulfide. All right, so here we're going to have x, here we're going to have x, because 0 plus x is x. So we have this minus x is our equilibrium. All right, so now if we substitute these in for our Ka expression, we're going to have x times x over 0.050 minus x. So all we did was we substituted in these equilibrium values from our ice chart into the equilibrium expression. All right, so if we simplify this, and this is all equal to 9.1 times 10 to the negative 8, because this is the Ka for hydrogen sulfide. All right, so if we simplify this, we're going to see that x times x can become x squared, okay, over 0.050 minus x is equal to 9.1. So we only have one variable here. We can solve for this x. All right, so what I'm going to do first is show you the beauty of the TI Inspire CAS. Now, you have to have the CAS in order for this to work, because this has algebraic functions solving. So let me show you how that works. So if we press menu and we go to algebra, which is 3, okay, oops, because I was pointing back and forth, it did that. So I'm going to delete. So menu 3, 1, see 1 is solve. I'm going to put in this expression. So box over a box. So I'm going to put in this expression right here. X squared divided by, so I'm going to have x, here's my x, and I'm going to do x squared, okay, divided by 0.050 minus x. Okay, so I'm just putting it in exactly as it's written. Okay, equal, so I'm going to hit and put my cursor here now, is equal to, then I'm going to put in that Ka value and make sure at 9.1, 10 negative 8. So 9.1 times 10 EE to the negative 8. All right, so here is that expression. So on the TI Inspire CAS, what you're going to do now is put in a comma, and that means solve for, that comma is the code for solve for x. So right here, you're telling, here's the equation, solve for x. And when I hit enter, it's going to solve for that. Now, since the quadratic equation was used in solving this, we have a negative and a positive value here. We're only concerned about the positive value. So x is equal to 6.7408 times 10 to the negative 5th. Okay, so 6.7408 times 10 to the negative 5th. All right, so that's how you do it if you have your CAS, Inspire CAS. All right, so most of us don't have that. That's just the reality. So the easy way to solve this is without using the quadratic equation, because that gets messy. This x value right here is going to be so small. See, this is so small. This is a very small number. So if I were to write that out in standard notation, it's to the negative 5th. So 1, 2, 3, 4, 5. It's this number. Okay, so we have 0.000067408. This number is so small that when we take this number, 0.50, and we subtract this from it, okay, it's not going to significantly change it's not going to change at all our significant digits. Okay, So what we can do is we can assume that since this is so small, it's not going to affect this value. Let's ignore it for now. Okay, so I'm going to ignore that. Once I ignore that for now, this now becomes a much easier equation to solve, right? So we have x squared. Let's get rid of our 0.050. So I'm going to pull it to this side of the equal sign. Now, since we're dividing here, when we pull across, what we have to do is the opposite function. So we're going to have to multiply both sides by 0.050. When we multiply this side by 0.050, it gets rid of it here. And so we multiply it here. So x squared is now equal to 9.1 times 10 to the negative 8 times 0.050. Okay? Now we have to get rid of this exponent here. So x squared is equal to this. Why did I write another x there? Sorry. All right, so x squared is now equal to this value. So to get this x squared pulled across the equal sign, we're now going to have to take the square root of this value. So this is going to be equal to the square root of this. That gets rid of our exponent of 2 there. So now this is x is equal to this function. All right, so I'm going to go back to my TI Inspire, and I'm not going to use the solve function this time. I'm just going to solve for that equation. So we have the square root of 9.1 times 10 to the negative 8 times 0.050. That's what we're solving for. So when we press enter, we see right here 6.74. Here we have 53688 times 10 to the negative 5th. Okay, so I'm going to write this down, 7453. Okay, so we have 6.7453 times 10 to the negative 5th when we do it without using the quadratic equation. All right, so here are my two answers. Now remember, I told you that when we do this, it's not going to affect our significant digits. So this is the value for x. Let me just go ahead and clean up my area a little bit right here so I can write this down. So what do we have? How many significant digits do we have in our given that we're given? We have 2 significant digits right here. So these 2 zeros don't count because they're leading zeros. Here's a trailing 0. That trailing 0 is going to count as significant because we have this decimal here. So we have 2 sig figs. So if we go over here and look, here's 1, here's 2. So we're looking at the 4 to see if it rounds that 7, and it does not. Okay, so for our answer down here, we have 1, 2. Again, we have a 4 here. So this part doesn't even matter. So you see here, we do get the same answer. However, if you have a CAS, if you get a CAS and you calculate this, this is the more accurate calculation. So occasionally, and we're talking very occasionally, this number right here may be just a little bit different by 1. So see, if this had gone up by just 1, then we would round this to an 8. Okay, but it didn't, so that's 6.7. Now you're not going to be docked and you're not going to be counted off at all if you show your work like this and you've done your work properly, but you just missed the answer by a 0.1. Okay, no one is going to count off for that. No one ever. I mean, even if you take AP chemistry, they're not going to count off for that because you've shown all your work, how you got to this, and it was correct. And if it's a multiple choice, they're not going to put these 2 answers that close together on a multiple choice for you to choose between those. It's just not going to happen. Okay, so even if it is a multiple choice, you'd be able to choose the right answer. Okay? All right, so we just solved for x. X is, and let me go ahead and write this down here since I've got this all messy. X is equal to 6.74 times 10 to the negative fifth. All right, so now let me go ahead and erase a lot of this over here. All right, so if x is equal to 6.74 times 10 to the negative fifth, that is what we would put here. So if I erase this, and this is 6.74 times 10 to the negative fifth, okay, of course, that very exact same thing is going to go here. And we can calculate this. So 6.74 times 10 to the negative fifth. And I'm going really, really slow on this problem and explaining a whole lot because it's our first problem that we're doing in this section. Normally, it would not take you this long to work out this problem, and I won't take this long on future problems to work it out. I'm just really explaining here so that I can make sure that you understand everything that's happening. All right. And so let's calculate this. 0.050 minus 6.74 times 10 to the negative fifth. All right, so when we go to our calculator, 0.050 minus 6.74 times 10 to the negative fifth is going to give us a concentration of 4.99 times 10 to the negative 2. Okay, so this is 4.99 times 10 to the negative 2. Let me go up here now and just put this number in here as the equilibrium. Okay, all right, so now we have our ice chart all filled out, and we can now use all of this information to just nicely answer this question that we have. And what was the question? What is the pH? So we're calculating the pH. All right, so pH is equal to the negative log of the hydrogen ion concentration. So the only bit of information we need here is this right here. So we solved for X, that's the hydrogen ion concentration. We don't care about this, and we don't care about this. Okay, so we only need to get the negative log of 6.7 times 10 to the negative fifth. Now I rounded this to our 2 significant digits that we need. Okay, all right, so going back to our calculator one more time, negative log, this is base 10, of 6.7 times 10 to the negative fifth, okay, 4.173. Okay, so this is 4.173, 2 sig figs. So this 7 is going to round this to 4.2 is our pH, okay? So that's what that number is right there in the corner. That's the correct answer that we should be getting for this. And so I just verified that we did this correctly according to the key. All right, pKa and pKb. So our K values are very small numbers. So if we look at our Ka chart, and you know what, I'm just going to go back to this. So here are our Ka values. Okay, these are very small numbers, 10 to the negative 7, 10 to the negative 10, very, very, very small. It's really hard to look at these Ka values and say, compare the strength of, say, this acid to this acid. It's very hard to do that because these values, we just don't comprehend that in our brain. So pKa and pKb were developed, okay, to help us cope with these very small numbers. Okay, and it says they're very hard to compare, just as I said, because they're written in scientific notation. But if we take the negative log of those numbers, they become manageable, comparable, understandable in our brains. So just like we take the negative log of the hydrogen ion concentration, so negative log of the hydrogen ion concentration is pH, right? pH. So P is really the negative log of this. If we take the negative log of our Ka value, we're going to get pKa. Okay, so it makes these numbers understandable. So here we have our acid. And I'm going to explain just a moment what the conjugate base means. So for this acid, here's our Ka. If we take the negative log of this number, we're going to get 1.23. Okay, and so here we see H3PO4. Here is the Ka value. If we take the negative log of that number, we get 2.12. So now we can compare these two numbers. Okay, so what I'm going to tell you is for acids, okay, when you take the pKa, the smaller the value, the stronger the acid. Okay, the stronger the value, the stronger the acid. Now, if I were to ask you the question on a quiz, which one of these is a stronger acid? And you have your Ka chart available. All you'd have to do is take the negative log of the Ka values. You get these two numbers. Which is the stronger acid? Okay, it's the oxalic acid. 1.23 is smaller than 2.12. So oxalic acid is stronger than H3PO4. Okay, phosphoric acid. So that's the importance of the pKa and the pKb. Okay, so that's what this chart is explaining. All right, so let's go back to talking about the dissociation equation, the conjugate base in conjugate acid. All right, so I'm going to erase this just so I can talk about this. So here's our equation, H2S plus H2O yields HS plus H3O. So this is our acid right here. Okay, now up to this point, we've been talking about just the theory of acids called Arrhenius acids and Arrhenius bases, where all of your Arrhenius acids start off with H and they have some kind of ion that it's bonded to, like HCl, H3PO4. Okay, in this next theory of acids, and this is called Bronsted-Lowry definition of acids and bases, not all acids are begin with the letter H. Okay. Also, in the Arrhenius definition of a base, we have anything that ends in OH. So, like NaOH. In this Bronsted-Lowry definition of acids and bases, they do not end in OH. Okay. So here's a new theory of acids and bases. And in the Bronsted-Lowry theory of acids and bases, okay, write this down, an acid is considered a proton donor. Okay, so remember a proton is just a positive proton in hydrogen. So acids are proton donors. Bases are proton acceptors or hydrogen acceptors. Okay, so hydrogen donors and hydrogen acceptors. All right, so if we look at this right here, this is an acid. And when this gives up its proton, okay, it forms what's called a conjugate base. All right, so this acid lost a proton. Okay, so it was H2S. It becomes HS. It lost its proton here. This is called the conjugate base of this acid. So it's this acid without a hydrogen. So it used to be H2S. Now it's just HS. Now this can go backwards too. So if we start off with HS, okay, if this accepts a hydrogen to become this, then here is our base. This is now written in this direction. So we're just taking this equation and we're going in this direction. This is now considered your base, and it accepts a hydrogen to become this. So this is our conjugate acid now. Oops, right here, conjugate acid. All right, so here's our base, here's our conjugate acid. It's the pair that goes with this base. So when this base accepts this hydrogen, it becomes a conjugate acid. Okay, so that's the definition of the Bronsted-Lowry. So here, if we have an acid, what is the conjugate base of this acid? Well, let's think about it. Acids are hydrogen donors, so it's going to be this exact same thing minus one of the hydrogen. So it's just going to be HC2O4. Since we lost a positive charge, this is now going to be negative because it was neutral here. So we lost a positive, now it's a negative. Okay, so I'm going to go down this list, so we're going to do the conjugate bases of these. Okay, before I explain about how to get Kb from Ka. Let me just erase this. Oops, I didn't want to do that. So let's go back one. I just wanted to, did it again, erase this. Okay, all right, so here we have H3PO4. So we're going to rewrite this. It's conjugate base minus one of the hydrogens, so it's going to be H2PO4, and it's a negative charge because it was neutral here. All right, so minus a hydrogen here, this is going to be NO2 minus. Okay, H2CO3 is now going to become HCO3 minus. H2PO4 is going to become HPO4. Now this was already a -1, so it's going to gain another negative charge. So it's going to be -2 here. Okay, NH3, and it was a positive, so we're getting rid of that positive, so now NH3 is neutral. And this is going to become CN negative. All right, so here's the conjugate base of all of these acids. It's just this acid minus one of the hydrogens, and then the appropriate charge for that. Okay, all right, now let's talk about how we can get a Kb value from a Ka value, and that's going to be very important. So Ka times Kb, these two values equal 1.0 times 10 to the negative 14th. Okay, if you don't believe me, just multiply these together and you're going to get some number around 1.0 times 10 to the negative 14th. So we're going to use this concept of the hydrogen or the acid concentration times the base concentration is equal to 1.0 times 10 to the negative 14. If we rearrange this, we're going to see that if we take our 1.0 times 10 to the negative 14 divided by whatever we have. So here we have our Ka. See, our Kb is missing here. So if we take this divided by that 5.9 times 10 to the negative 2, okay, we're going to get the value for OH. Right, so it's just algebraic rearranging. So let me go ahead and do that just to show you. So 5.9 negative 2. So if we go over here and we do 1.0 times 10 to the negative 14th, and we divide this by 5.9 times 10 to the negative 2. I'm just going to verify, go back over and verify that's 5.9 times 10 to the negative 2. It is. Okay, we're going to get 1.69 times 10 to the negative 13th. 1.7, that's just rounded, times 10 to the negative 13th. So that's how we get our Kb value when we're given our Ka. So you're going to see here in a moment why that's important. Right, same thing here. 1.0 times 10 to the negative 14th divided by 7.5 times 10 to the negative 3 is going to give us 1.32 times 10 to the negative 12. All right. Now, pKb, there's two ways to get that. If you solve for the Kb, all right, if you solve for the Kb, then the way we get pKb is just take the negative log of this value. It's negative log of this value. Okay, and it's going to give us 12.77. Now, it's just like pH. There is no difference. It's exactly like pH. Okay, if we don't have this value, 1.7 times 10 to the negative 13th, we can take our Ka and take the negative log of that. Okay, so the negative log of 5.9 times 10 to the negative 2 is going to give us our pKa, right? That's going to be equal to 1.23. So if we want to solve for the pKb, all we have to do is take 14 minus 1.23. That's going to give us 12.77. Okay, so it's the same thing as the pH. This is just working with Ka and Kb. So you can get all of these values. So on your problems homework sheet that you have a table like this where you're solving these values. It may be this exact table, as a matter of fact. So that's how you get those. All right. So why is that important? Oh, one other thing that I want to mention to you is, and you might want to write this down, weak acids make strong bases. Okay. Weak acids make strong bases, and vice versa. Strong acids make weak bases. Okay, strong acids make weak bases. Okay, and that makes sense because here we have a very strong acid. Okay, strong acid makes a very weak base. Okay, strong acids make weak bases. All right, so for this problem, it says that we have a 0.100 molar solution of acetylsalicylic acid, which is the same thing as aspirin. And this is found to have a pH of 2.27. Okay, so that's going to be important. Circle this as our given. Okay, and here is also a given that we have to make sure that we recognize. Find the hydrogen ion concentration, the Ka, conjugate base, pKa, pKb, and Kb for this acid. So there's a lot that we're having to solve for. And the reason I put this in here is so that I can show you that you can solve for all of these with just limited information. Most questions that you're going to have, it's going to say solve for the hydrogen ion concentration, or calculate the Ka, or what is the conjugate base of acetylsalicylic acid, etc. It's only going to ask you for maybe one or two things. But here on this problem, we're going to do it all. All right, and so it tells you the formula for acetylsalicylic acid is C8H7O2COOH. So I'm going to write that down, C8H7O2COOH. This is an acid. Okay, now, this doesn't conform to our old definition of acid that we're using, the Arrhenius, because it doesn't start with an H. It doesn't begin with an H. Okay, so this is a Bronsted-Lowry acid. It's going to donate, okay, so remember the definition of an acid, it's going to donate this hydrogen to water. Okay, so we're going to have C8H7O2COO. It's going to take off a hydrogen and donate it to water, making H3O, but we're going to do the shortcut and just write H. All right, so right off the bat, we can identify the conjugate base. This is the acid. The conjugate base is going to be right here. So I'm just going to put conjugate base, right? So that's the conjugate base. All right, so from this, just basically we can hardly get any of the other stuff. I'm going to go ahead and continue using glues where I list out all of the information. So in our ICE chart, we're going to have ICE, initial change equilibrium. Okay, so we're going to have a section for that, and a section for this, and a section for this here. Okay, so this is going to be the column for my H. This is going to be the column for the conjugate base. And of course, this is the column here for the aspirin. So it tells us that we're beginning with 0.100 molar solution. So we can go ahead now. Let's just fill out our ICE chart. I don't know where to begin with this. I don't know where to start. All right, so just do what you can. Fill out your chart. So this is going to initially have 0 concentration. So this, when it dissociates, it's going to go down by some value. We don't know how much. It's just going to go down by, let's call it X, down by X. Since this is the molar ratio is 1 to 1 to 1, this is going to go up by some value of X. And when we say X, we're talking about molarity, molars, minus X molarity, molar. This is also going to go up by X because it's 1 to 1. So what are we going to have at equilibrium? We're going to have X, X, and 0.100 minus whatever X is. All right, so we have to have some way to solve this. Well, let's look at our other piece of information here. The pH is equal to 2.27. So what is the pH? It's the value of the strength of the hydrogen ion concentration. So from pH, we can calculate the hydrogen ion concentration. Okay, so that's 10 to the negative pH. It's one of our formulas. So this hydrogen ion concentration, oh, look at this, can be plugged in right here. Okay, so if we take 10 to the negative 2.27, it's going to give us what our X is. Then we'll be well on our way. So let's do that. 2.27. Okay, so 10 to the negative 2.27. I'm going to make sure, double check. 2.27. Yeah, 2.27. Okay, so that's going to give us 5.37 to the negative third. Okay, 5.37 negative 3. So X is equal to 5.37 times 10 to the negative 3. Oh, look at this. There's the key right there. So I did get 5.37 times 10 to the negative 3. All right, so that's our hydrogen ion concentration. So I'm going to go over here and put in that this is our hydrogen ion concentration. Okay, let me erase this because I might need to write other things there. All right, so now we've solved for the hydrogen ion concentration. So what's another thing that we can solve for here? We need to get our Ka to calculate pKa. We need to get our Kb to solve for pKb. So the only thing that we can solve now for is the Ka. Okay, Ka is equal to the concentration of, and I'm just going to call this conjugate base because we already identified that. You know what? I'm just going to write it out. C8H7O2COO times the concentration of our hydrogen ion over, I need to clean this up a little. The concentration of our C8H7O2COOH. All right, so that's our Ka expression. Well, we know what this is, okay, because it's X, we know what X is. So we can substitute values in here. We can calculate this. All right, so this is going to be just simply X squared over 0.100 minus X, which is equal to 5.37 times 10 to the negative third squared over, let's go ahead and calculate this. So we have 0.10 minus 5.37 times 10 to the negative third. We get 9.46, 10 negative 2. Okay, 9.46 times 10 to the negative 2. All right, so now we have a math problem that's going to give us Ka. All right, so we have on top 5.37 times 10 to the negative 3. Let me make sure that I have that right. Yep. Times 10 to the negative 3. Okay. And I'm going to put in parentheses here because this needs to be squared over 9.46 times 10 to the negative 2. All right. And so our Ka value is going to be 3.04. 3.05 times 10 to the negative 4. Okay, 3.05 times 10 to the negative 4. Okay, see right there, the key says that the Ka, it gave us the Ka value in the key, so we are doing this correctly. So Ka is equal to 3.05 times 10 to the negative 4. All right. So let's erase all this so that we can have this room for calculations of the other things. All right. So going back to what we previously talked about, if I have the Ka, I can now calculate the Kb because 1.0 times 10 to the negative 14th divided by our Ka, 3.05, times 10 to the negative 4th, it's going to give us our Kb. Okay, so this will give us our Kb. All right, so let's do that. 1.0 times 10 to the negative 14th, times 10 to the negative 14th, divided by 3.05 times 10 to the negative 4, 3.28, 10 negative 11. So that's 3.28 times 10 to the negative 11. All right, so now we can calculate pKa and pKb. All right, so take the negative log of our Ka value to get pKb. So I think I said that wrong. pKa is equal to the negative log of our Ka value, which is 3.05 times 10 to the negative 4. Okay, so let's do that. So negative log 3.05 times 10 to the negative 4. And this is going to give us 3.52. Okay. Now there's two ways to get Kb here. Can you think about the two ways? One way is 14 minus 3.52, or you can take the negative log of our Kb value. That's going to give us pKb. So let's just do both and see if we get the same number. All right, so 14 minus 3.52 is 10.48. And the negative log of 3.28 times 10 to the negative 11 3.28 times 10 to the negative 11. Okay, 10.48. Is that what we got? It sure is, 10.48. Okay. All right, so we calculated Kb, pKa, and pKb for this acid. All right. One of the compounds responsible for the odor of herring brine is methylamine. There's the formula. Its Kb is 4.4 times 10 to the negative 4. Calculate the pH of a 0.50 molar solution of methylamine. All right, so let's write out our equation first of all. We have CH3NH2, right? And it says that the pKb of this is 4.4 times 10 to the negative 4. So this is a base because it's given us the Kb. If it gives you the Kb, it's a base. If it gives you the Ka, it's an acid. So it doesn't come right out and tell us this is a base, but we can glean that from the information. So if this is a base, it's going to be added to water. This is going to accept a hydrogen. So we're going to get CH3NH3 plus OH. Okay. It accepted a hydrogen from water, so it has another hydrogen here, OH. Okay, so let's go ahead and draw our ice chart because this is a weak base. So now we're going to have an ice chart for this. So I know that we're working just with weak acids and weak bases, but if you saw this problem on a test and say it was a final exam or some kind of, AP exam, then if it's asking you to do all this, it's not going to say, use this method. Okay, it's a weak base. We know it's a weak base because it's not on the strong base chart. So this is one way to go about it, to think about that. All right, so it says that we're starting off with a 0.50 concentration. We calculate the pH. The Kb is 4.4 times 10 to the negative 4. 4.4, 10 to the negative 4. Make sure you get that written down correctly. Okay, so we can start this because we have all of our information written down. So initially we have concentrations of 0 here. This is going to go down by some value of x. This is going to go up by some value of x, up by some value of x. We're going to end up with x, x, and 0.50 minus x here. So it gives us our Kb value. So 4.4 times 10 to the negative 4 is going to be equal to, shortcuts, I'm cutting out steps, x squared over 0.50 minus x. So we can solve for x now. So let's go to the calculator. I'm going to use solve. So we have here x squared over 0.50 minus x. I think that was it. Let me make sure. 0.50 minus x. That's going to be equal to our Kb value, which is 4.4 times 10 to the negative 4. So 4.4 times 10 to the negative 4. Solve for, comma, x. If I did this right, I should get 1.46 times 10 to the negative 2. Okay. 1.46 times 10 to the negative 2 is x. All right. X is the OH concentration. So what is it telling us to solve here? Calculate the pH. That's the only thing we need to do. So if we have the OH, we can calculate the POH. And if we have POH, we can calculate pH. All right, so the OH concentration is 1.46 times 10 to the negative 2. So if we take the negative log of this OH concentration, that's going to give us POH. Okay, so that's going to be equal to negative log of 1.46 times 10 to the negative 2. Okay. 1.84 All right, and with 1.84, POH plus pH is equal to 14. So if I take 14 minus 1.84, I should get pH. So 14 minus 1.84, 12.16. Oh, didn't mean to do that. So the pH is 12.16. Okay, the key says 12.17, but that's probably because we used our X solve on our CAS. So let's do this again, not doing the X solve, like if you don't have the Inspire. So I'm just going to write 12.16 is what I got here. All right, so let's go back to this point. All right, so ignore this because it's so small it's not going to affect the significant digits. So let's go back to, this is going to be x is equal to the square root of 4.4 times 10 to the negative 4th times 0.50. So that's our equation. So let's see here, 4.4 times 10 to the negative fourth. Oops. Let's go back. I have to take the square root of that. So 4.4 times 10 to the negative fourth times 0.50. All right, so that's going to give us 1.48 times 10 to the negative 2. Okay, and that's our OH concentration. So if I take the negative log of that, and I'm just going to put in the answer. Oh, hold on. Okay, so here, just put in your answer, which is that function on the calculator, answer, ANS. So that's going to give us 1.83. So POH is equal to 1.83. So 14 minus 1.83. 14 minus 1.83. 12.17. Okay, 12.17 right here. All right. So that's it for Ka and Kb in this section. Please make sure you slap that like button right across the face. Make sure you give me a thumbs up and make sure that you click that notification bell so you'll know when I put up more videos, maybe working out some sample problems for you.